Hello everyone, welcome to our talk. Today we are going to talk about the bijective projection in a shell. My name is Zhengshi Jiang, and this work is a collaboration together with Cecile Schneider, Dennis Sorin, and Daniele Panozzo from New York University. We love meshes, but often I look at a mesh and say, I want something a bit different. Maybe it's for better triangle, or coarser, aligning to curvature, or denser. This adaptation of meshes for downstream applications is what we call remesh. Once you do remeshing, you will have several different meshes. Now we want to use the new ones, but the question arises: how to assign the colors, materials, or boundary conditions onto the newly created ones? The meshes approximate the same shape, so they should be close by in space. Therefore, our first attempt is to perform closest point query. For each point on the original mesh, find which point is the closest on the new one. For smooth surfaces, this corresponds to Euclidean or orthogonal projection. More specifically, if you trace along the surface normal, then it might hit another mesh if they are close by and smooth enough. Discrete surfaces like triangular meshes can be a bit more challenging, since the normals are now constant per triangle. And people have proposed to modify the normal field to make it continuously varying, like foam shading. This projection paradigm provides a way to query the corresponding points between meshes with a simple operation of ray triangle intersection. But there is no guarantee that how far the ray will go and whether there will be some forgotten and missing region. To put it more precisely, the mapping is not continuous nor bijective. So let's look at some of the alternatives. One interesting topic that has been studied for a long time is cross-parameterization. Basically, you need to map two shapes onto some common abstract domain and optimize for better matching. However, this approach requires and depends on a consistent initialization. However, in the context of remeshing, we can also perform tracking. During each operation, for example, collapsing an edge, we can keep track of the local map of the one-ring neighborhood before and after this step. However, whenever you want to evaluate such a map, it requires a history of operations and therefore is commonly only used for algorithms with limited number of them. Another intriguing alternative, though, is to use high-quality intrinsic bases to perform computation instead of remesh. However, this approach is currently mostly limited to surface-based problems that don't require an embedding. So we decide to revisit the projection. To better understand the problem of bijectivity, we look at our two meshes projected onto each other. Taking a closer look at the path of projection, it can be seen as a vector field in 3D, and we can look at this vector field design problem in the space. Now, if we try to extend the vectors globally without too much care, intersection of path will follow eventually. But since during remeshing, the meshes don't usually go too far, we can restrict our view in the vicinity of the surface region. And we use the structure called shell. The shell structure is frequently used in graphics and engineering, for example, in data interpolation, volumetric texture, and boundary layer meshing. To describe our construction more precisely, our shell is a region around the input surface. It is further tessellated as a collection of prism cells. For easier computation, we further subdivide it to linear tetrahedra and assign a constant direction for each tet that is pointing to the top. Now, with this structure, we can associate two meshes in the shell. We look at one prism more closely. For an arbitrary point on one surface, it can follow along the direction of vector field to travel until it hit the other surface. This provides us a way to associate any point on these two surfaces. But how can we make it bijective? The first condition is that a volume of all the tetrahedra should be positive. Otherwise, the vector field will locally fold onto itself. Second, the surface we're considering should pass through each cell only once. However, even if there's only one component in the cell, it could bend and wiggle arbitrarily. We prevent this from happening with one simple local condition on the normal of the triangle mesh. Namely, we ask that the vector field direction and triangle normal to form an acute angle. In other words, their dot product will be positive. With this condition satisfied, we're able to show that we finally arrive at a mapping that is continuous and bijective. Also, since our operation based on ray triangle intersection, it's also easy to evaluate. What's more, our vector field is characterized implicitly by the connectivity and the position of a mesh, so it can be easily controlled and optimized. And also, we can finally associate more than two meshes, as long as they're in the same shell and satisfy the condition on the normals. And we also show that whenever the conditions are satisfied, the meshes inside will be free of self-intersection and suitable for volumetric computations. Now let's talk about how to make this shell. We're going to illustrate the pipeline in 2D and explain some detail in 3D later. Starting from a manifold mesh without self-intersection. The first stage is extrusion to find an initial valid shell with respect to the input surface. After such an initial shell is constructed, we can further optimize and simplify to get high-quality thick shell. During the first stage, we show that the problem of constructing an initial shell can be reduced to finding a direction for each vertex. We simply ask the direction to form an acute angle with the adjacent normal. The optimization stage is an analog of mesh optimization. We perform local operations on the bottom and top surfaces simultaneously while preserving the validity of the shell. Now let's move on to 3D. In 3D, our shell is composed of cells in such shapes of triangular prisms. Each layer of prism can be decomposed into 3 tetrahedra with vector fields directions naturally assigned. During the stage of extrusion, since now there are more neighboring triangles to a vertex in 3D, we will consider more triangles. Again, we still ask the angle between the triangle normal and the direction to be acute. We also optimize to get a direction that maximizes the smallest one of these angles. Interestingly enough, there are geometric configurations where this direction does not exist at all. Here, adjacent to the red dot, 2 triangles have their normal opposite to each other. We call them singularities. More detail on the handling of this case can be found in our paper. As for the shell optimization, a mesh in 3D has more degree of freedoms, and we perform more operations accordingly on the connectivity and positions to optimize the shell. Now we can perform edge collapse, edge flip, and vertex smoothing in the shell. Overall, our pipeline can transform a triangular mesh into a thick and coarse shell. Let's see an example of how this shell could behave in practice. We perform a series of edge collapse on the surface alone, and we get a coarse one. However, the coarse mesh has self-intersections and flipped triangle normals as marked out by pink. We can use our shell to simply discard some of these operations whenever an operation will violate the shell constraints. In the end, we get a slightly denser but well-oriented valid mesh. Since the algorithm was designed with robustness in mind, we are able to verify that our pipeline for constructing the shell succeeds on more than 10,000 models in the wild. Let's have a look at some of the applications we can now achieve. Starting from a triangle mesh with many slivers. Different triangles here are indicated by different colors. We would like to test the elastic response by stretching these two ends. However, the quality of triangles would give a hard time for conformal tetrahedral meshing and subsequent volumetric finite element simulation. Instead, we build a shell. Inside the shell, we remesh to have a high-quality mesh with bijective mapping to transfer the boundary conditions. And now we can perform the tetrahedral meshing and FDM to get a simulation result. Again, use the exact same mapping induced by the shell, we can transfer back the solution as a displacement field. And therefore, we have a high-quality simulation on a low-quality mesh. We can also use our construction to assist mesh Booleans. The union of two meshes can be low quality and dense, especially around the interface. We build a shell and optimize and simplify the mesh inside the shell to have a high quality and coarse representation, with the colors bijectively and exactly preserved. Our projection can also be used to build displacement maps. A typical pipeline decimates the input mesh and densely sample on this simplified mesh to use standard projection to reconstruct the geometry. However, if you look at this close enough, because the standard projection is not continuous nor bijective, there are artifacts like tearing. If we use our projection, the reconstruction will be smooth. A happy side product of our construction is volumetric texture. Here, starting from a triangle mesh, we build a simplified shell where we can bijectively transfer the UV coordinates from the input. If we place a chainmail texture on the UV domain now, we can construct a highly complex shape in the shell space. Here are some of the items we have yet to achieve, and I believe they are very interesting future directions to pursue. Our construction relies on close-by meshes, and it will be very interesting to extend similar construction to build an intersurface mapping. Next, the current approach to preserve feature or an open boundary is by fixing them. And allowing them to simplify can be more desirable in many applications. Third, the construction procedure is robust but cannot be used in interactive application because of the cost. For example, this shape with 180,000 faces can take up to 10 minutes to process. However, such time in meshing is far from being a bottleneck in a volumetric finite element simulation pipeline. Let's summarize. In this talk, we propose an algorithm to build a shell and the bijective projection operator inside. Furthermore, we present a remeshing algorithm that is able to preserve correspondence and attributes from the input bijectively. We also open source our implementation and would very welcome for you to try it out. Thank you very much for the attention.